Hello! I'm here today to nerd out with you about the Doppler effect. The Doppler effect is a really cool topic in my opinion because we can learn a lot about our world, like weather and I think information about our own body, as well as the universe using the Doppler effect. The Doppler effect is all about how things move. So the Doppler effect is defined as a perceived change in frequency due to the relative motion between the source of a wave and its observer. So it's all about how something is moving relative to our motion. So we'll start with a simple example of a car horn. So hear that one more time. And of course, the sound gets louder as the car approaches and quieter as it moves away. But what we're listening for is the shift in the note that the car horn makes. So at rest, the car horn just makes one note that doesn't change. But if you listen really carefully, you can hear an increase in pitch and ee just before the car approaches the camera, and an ooh, a decrease in pitch as it moves away from the camera. So let's hear that again. So how does this work, or like how does this make sense? So if we think about our source of sound as something that is creating waves in all directions, like we can see here. So if it's not moving, the sound waves move out in all directions away from the source, and these white lines represent consecutive crests of a wave. So the visual is similar to like a little bob or a cork bobbing up and down on a pond, and the source of sound, when it starts to move, catches up with the previous crest that it made in the direction of motion. So as we move, we can get faster and faster, and we can see that in front here, we're kind of catching up with the waves that we produced before, the crest that we produced before, and behind, we're actually moving away. The newest crest is being made kind of further away from the previous crest. So we can exaggerate that. And this is a really nice visual that I actually like to draw every time I'm thinking about a Doppler effect problem. So we have the wave fronts bunched together in front of the moving source, or when the source is moving toward the observer. It's about relative motion, so actually you could be moving toward the source of the wave, or the source of the wave could be moving towards you. And in that case, we get this high frequency perceived note, the E, and the wavelength, it's pretty clear here. The distance between the lines, or the distance between the crests, decreases. Behind, the source is moving away from you, or you are moving away from the source. We see a very dramatic increase in wavelength and a decrease in frequency, the ooh that we hear with the car horn. Now with light, this actually appears as a shift in the frequency of light. So long wavelength, low frequency light is red. High frequency, short wavelength light is blue. So I did color code these, red for moving away and blue for moving toward, because that's what we see as a red shift and a blue shift when it comes to light. And I took this picture of my bumper sticker that will go down with the construction last Tuesday at 7 in the morning. It says, if this sticker is blue, you're driving too fast. So it's a red sticker, but if you're driving really, really fast, like close to the speed of light, faster than you would normally be driving on the highway, this sticker would appear to be bluer. And if you're driving way fast, then it might even actually look blue. But it doesn't just like turn blue, it looks to be a color that is bluer than the original color. So if the original color was red, a color that's a higher frequency than red would be yellow or green. And then eventually blue and violet. So this kind of begs us to think about pushing our limits here. What happens if you go too fast? For example, if we think about with sound, going back to sound, what happens if you go faster than the speed of sound? So looking back at our cool simulation here, which I've put in the comments section, or not comments, the description, if I play the simulation and I put it to a speed that's faster than the speed of sound, which is signified as 1 or Mach 1 in this simulation, we can see something interesting happens. So we're pushing, pushing, pushing. All these wavefronts are kind of getting up on each other. I'm really close to Mach 1. And then when I exceed Mach 1, what happens is I end up being a little bit ahead of my sound. So you end up with this bow shock, and it's really dramatic if you stretch it out. So there's this shock wave that forms from pressure. So again, we're talking about sound. Sound is a pressure wave, and so when these crests or areas of high pressure get all up on each other, the air is actually compressed and has a really high pressure. And so we can see this in this video where this meteor is going to go over these houses, and it's actually moving faster than the speed of sound over those houses. So the speed of sound in the atmosphere. So it will pass by, it is moving so fast that it creates this shock wave, this sonic boom, and we'll actually see the sonic boom pass by the houses as well. It'll shake some snow off the roofs, and it'll kind of mess with the audio. So this is a significant pressure wave. It kind of sounds like a boom, and you can see this in videos as well. So if we look at videos of supersonic aircraft, we can actually see a bow shock, and the shape is seen really easily in this simulation. We can see this bow shock manifest itself as a cloud. So the area of high pressure causes water molecules to condense, and it looks like a cloud. Now, this actually happens in space, which is pretty cool, and we gotta pause this because we've talked about how space is a vacuum and no one could hear you scream in space, but I'm telling you that there's a speed of sound in space. So in reality, space isn't entirely empty. There's planets and us and stars, and then there's these clouds of molecules. Now, compared to the atmosphere, space is very, 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 very empty. It's very close to a vacuum, but it's not entirely empty in all places. So we actually can exceed the speed of sound in space, or things can exceed the speed of sound in space, and that can create shocks. And that's a whole field of astronomy, modeling the hydrodynamics of those shocks and how they work and how they propagate through space. But one really interesting image from space is this one of Zeta Ophiuchus, the runaway star. And this star here is moving to the right across this picture at 24 kilometers per second. And as it's doing this, it is putting out gas and dust, and it's moving through a cloud of gas and dust, and it creates this bow shock. And we actually can see the similarity here between the cloud bow shock around a supersonic jet and the cloud-shaped bow shock around a supersonic star. So this is taken from the Spitzer Space Telescope, which primarily looks at the universe in the infrared, and we can see very red emission coming from this area because this is where the most energy is. So this is where it's the highest pressure, and things are a lot warmer in this region than they are further out. So really interesting bow shock. There's a few more close to home applications of the Doppler effect. If we combine it with the idea of reflection, so the idea that when a wave bounces off of something, it comes back, we can actually determine how things are moving, how fast things are moving. And this is actually how police officers determine how fast you're moving. And I did think that it would be really difficult for a police officer who's driving at you to figure out how fast you're moving, but they actually have figured that out with technology. So what happens is the radar, which is a radio wave that the police officer sends at your car, so there's like radar, speed gun, they send a radio wave to your car with a known frequency. It reflects off your car and they perceive the frequency that it comes back to the receiver at. So if there's a high frequency shift, then the car is moving towards the police officer. If it's a low frequency shift, the car is moving away from the officer. And based on the size of the shift, you can actually determine how fast the car is going relative to the officer's motion. So if the officer knows how fast they're going and they tap these speed guns into their cars now, then they can give a pretty precise estimate of how fast you are going, even if they're coming at you. We also have Doppler weather prediction, which you may have heard of. And same idea, we have a radar sent to a cloud, like at a storm system, and it bounces back, and you can see if that storm system is moving towards you or away from you and how fast it's moving. And then I actually have what's called a fetal Doppler, or a baby Doppler, and this is a little ultrasound machine. So I put like ultrasound gel, so this uses sound waves, and it will produce the baby's heartbeat. So I can hear my baby's heartbeat and kind of get a sense of how she's doing, which is kind of cool. So those are some close to home applications. Some more spacey applications, because you know me and I love space, are the idea that we can tell how fast things are moving towards or away from us in space. So that's that same idea of the Doppler shift. This is how we know all galaxies are moving away from us. So the expansion of the universe is seen because every single galaxy has stars that emit light with certain frequencies. So we know the stars fuse hydrogen together, and we can see in a continuous spectrum some absorption of light at a frequency that corresponds to an energy level transition in a hydrogen atom. So we expect to see these bands of no light. This is the at rest position here, when something is not moving away from us. But when something is moving away from us, this known predicted hydrogen alpha emission or absorption line is actually farther into the red part of the spectrum. So this is how we know the universe is expanding in all directions away from us and how fast it's expanding, because we can see this redshift of expected frequencies of light. This is also how we can know there are planets around other stars. So it's one way of detecting planets around other stars. As a planet goes around a star, they orbit its center of mass, and it causes a star to move as well or wobble. So if a star-planet system is lined up in a way that's just right, so it will either move towards us or away from us, we can see that the spectrum of the star is periodically red-shifted when the object is moving away from us, the star is moving away from us, and blue-shifted when it's moving towards us. And we can actually learn a lot about the planet and star system by measuring how great this shift is and the period of the shift. So this is a little picture, and I'll post some videos in the description below. So this picture shows a top-down view of a star, represented in red, planet system orbiting a mutual center of mass. So when the planet and the star are moving perpendicular to our line of sight, there is no shift, but when they're moving along our line of sight, we can see a redshift as the star moves away from us, so that these like double lines here are in the redder part of the spectrum, and we can see a blue shift as the star moves towards us, and these redder lines are kind of towards us. Notice it doesn't mean that the star turned blue or turned red. It's just a very small shift toward the blue end, or the higher frequency, shorter wavelength end of the spectrum, or a small shift towards the lower frequency, longer wavelength end of the spectrum. So the Doppler effect can tell us a lot about a lot of things. With light, it can tell us how the universe is expanding. It can tell us about the size and orbital radius of planets around other stars. And it can tell us about weather here at home, about how fast your car is moving and whether you deserve a ticket. And it can even tell us about the health of a baby that we haven't even quite met yet. So I'm using the field Doppler right now. I don't know if you can see the numbers on here. There we go. You can hear our heart rate. And it's a lot faster than mine.